Hi. So in this episode, we'll discuss the correlated equilibrium. Okay. So remember that previously we talked about the interpretation of the mixed strategy Nash equilibrium, right? So basically, it's a representation of some steady state where each player's action depends on a signal that the player receives from nature, right? So because at the moment when some player is randomizing the strategies using the mixed strategy, so that signal or that the randomization is sort of from nature, right? So depending on the mood or depending on the some very random events, right? So that be could be regarded as the nature is like choosing the mixed strategies, choosing the randomness here, right? So that would be some interpretation for the mean strategy Nash equilibrium, right, at the steady state. Okay, so but in that interpretation, we know that the signals they're private and independent, right? So each player is actually uh, taking the mixed strategies and according to their uh, own private and independent signals, which could be regarded as receiving from the nature, right? So that's a one of the plausible interpretation of the mixed strategy, right? So let's write that down first. So a interpretation of mixed strategy Nash equilibrium. So it could be regarded as steady state, right? So it's more like a steady state in statistics, right? So you might need to make tons of experiments to get that steady state on average, right? So where each player's action, okay, depends on a signal, okay, received from sort of nature, okay, from outside, exogenously. Okay, so in this case, in this interpretation, the signals, okay, so this will be private and independent, okay. All right, so that's the previous stuff, right? So that's for the mixed strategy Nash. Okay, but in this episode, we're not going to continue on the other properties of mixed strategy Nash equilibrium, but instead, we're going to talk about the correlated equilibrium. Okay, so the difference is that, so let's consider what happens if the signals they're not private and not independent. Okay, so what if those signals, okay, which lead to the mixed strategies, so what if those signals are not private and independent? Okay, so that's what we're going to talk about in this video. Okay, so for example, in the game of the battle of sexes, okay, so both two players, either the man and the woman, okay, so both players they observe a random variable, so that takes each of the two values x and y with some probabilities, let's say a half, okay, equally. Then there will be a new equilibrium, okay, so where both players they choose back if the realization is x, and choose Stravinsky if the realization is y. Okay, so that signal could be regarded as something that is not private and independent, right? So they observe something in common. Okay, let's say if tomorrow could be sunny or rainy, and they made some sort of discussion and regarding the weather tomorrow, and say that if the weather will be sunny, then let's go to see Bach. Okay, so if in the other case, if it's raining, let's go to see Stravinsky. So that signal would be perfectly correlated to both players, right? Because that's a public signal. That's not private. That's public, and that's not independent. That would be the same, exactly the same one. So that's the opposite of independent, right? So, okay, so there'll be this new equilibrium, right? So where both players they choose Bach if it'll be if sunny, and Stravinsky if rainy. Okay, if Y. Let's say in this case. Okay, so given each player's information, okay, so the action would be optimal. Okay, so if the realization is X is sunny, then the band knows that the other player would choose Bach. Okay, so it would be optimal for this man to choose Bach at the same time, and symmetrically for the other case. Okay. All right. So, and later we'll come back to this example and give the numerical details for that. Okay. After we formally define the correlated equilibrium and to define the and give some propositions about that. Okay. So let's so in this okay. Now let's just take some notes first. All right, before we go ahead. So, for example, battle of sexes. Okay, let's say X, for example, sunny, and they all go to Bach. Okay, so if let's say 50-50, this would be some signal observed by both two people. So this could be rainy, and they go to Stravinsky. Okay. All right. So this could be so this is obviously public signal, and it's perfectly correlated, right? So this could be example, right? But let's consider some other cases. So it might also be possible that the players so they're observing the same random variable, but sometimes their information could be less than perfectly correlated, right? So their information that they observe could be somehow not that perfectly correlated. Okay, so let's consider example where there's a random variable that takes 3 possible values, okay, in a state space. It could be X, Y, or Z. Let's say sunny, rainy, or windy, right, or cloudy. Okay, so so that is the this random variable, and player 1 knows that only the realization is either X or it is an element of Y and Z. Okay, so player 1 could observe is either X or something in the other set, Y or Z. Okay, so but that player 1 cannot tell that it's Y or Z exactly, but just know that it's within that set. Okay, so the player 2 knows that it's either X or Y or Z. Okay, so that's player 2's what player 2 knows. Okay, so we call this as the partition. Okay, so this is obviously some partition for this X, Y, Z for this state space, right? So this information partition. Okay, so this would be a big set. So this is the information partition for player 1. This is for player 2. Okay, so that's some definitions, little definitions for that. Okay, so so under those assumptions, so a strategy for player 1 could consist of 2 actions, right? So one that so she uses when she knows that the realization is X, and one strategy that she uses when she knows that realization is something in Y and Z. Okay, so and similarly is the same thing for player 2, right? So symmetrically. So so player strategy would be optimal if given a strategy of the other player, okay, for any realization of his information, that he can do no better by choosing action different from the dictated by the strategy, right? So let's simply consider a specific a number or some random variables notations for this example. Okay, so let's say that to understand how the player is using the information in choosing some optimal action. So let's suppose that the probabilities of y and z. Okay, so probability of y would be this, and the probability of z would be something like this. So let's don't use those Greek letters. Let's say this would be something a. Okay, so probability of z could be b. Okay, maybe let's use b and c, right? Okay, so the player 2 strategy is to take the action a2. Okay, taking a2 if player 2 knows that the realization of the state is in x and y. Okay, if knows it's in x and y, so in this set. Okay, and takes b2 if knows it's z. Okay. All right. Then, if player 1 is informed that either x or y has occurred, then player 1 would choose an action that is optimal, given that player 2 chooses a2 with some probability. So that probability is just the probability of y conditional on the set y and z, right? So then player 1, okay, right? So if player 1 is informed that either y or z has occurred, okay, then chooses an action. Okay, so it should be an optimal action. Right, optimal action given that player 2 chooses a2, right, with probability of b over b plus c, right? So that would be just the probability of y conditional on, let's say it's the set of y and z, right? Okay, so, and that's a2 or takes b2 with the probability of the complement, right? So c over b plus c. Okay, so that would be a very also a very natural example of this. We'll know that would be called correlated equilibrium. Okay, so that would be example of if the two players, they receive some signals, but they're not private and not independent, but in addition to those signals, they're somehow not perfectly correlated. Okay, so there will be a general partition of that. Okay, so, and we can see that this partition, right? So that's actually very useful for us to model the correlation, right? The correlations between the let's say the signals, right? And if you have watched the previous videos about the multiple receivers information design problem, then or in the multiple standards information design problem, right? So it will be very useful to know that the actually the partition is actually very helpful to model those correlations, right, between the different signals that designed by different senders. Okay, so that's another story. Okay, all right. So now let's come back to the formal definition. So let's begin with that of the correlated equilibrium. Okay, so all right, definition. Okay, so a correlated equilibrium. Okay, so it's called correlated because those players, they have a correlated signal, right, to tell them how to take the action, right, of a simultaneous move game or a strategic game. Okay, now the players, action profile, utilities. Okay, so this has some ingredients. Okay, so the first part of this equilibrium is a finite probability space. Okay, omega and some pi. Okay, so this omega is the set of states: sunny, rainy, or windy, or cloudy. Okay, so this pi is just a probability measure. Okay, and you can refer to the previous videos for the probability measure. Okay. All right, and second, it has some other ingredients. So for each player I, so a partition, okay, pi. This p looks like the power set, right? But it's not power set, it's a partition here of pi, of omega, sorry, omega. So this will be I's information partition. Okay, so we're following strictly on the definition in the textbook of Osborne and Rubinstein. Okay, so third, so for each I, a function or a map is also part of this this equilibrium. So this sigma I, a function from omega to the set of ai, okay, and satisfying that. So if for some sigma I given omega, so it would be have the same value of sigma I omega prime whenever omega in some pi, okay, and omega prime also in this pi for some pi as the element in this partition. Okay. Okay. So this omega, this sigma I is I's strategy. Okay. And it's not finished yet. So for this function, we also so for those notations, we also need to satisfy something. Okay, so basically, you might have already guessed is that we need to satisfy some inequality to have those sigmas, they should give the optimal expected payoffs for the player, right? Other than some deviations. So such that, okay, for each I and each function, let's say tau, okay, so this will be some deviated function, not the original sigma. So this tau from omega to a, okay, for which tau I omega equals to tau I omega prime whenever, so the same thing, whenever omega and omega prime, they're both elements in pi for some pi as the element of this curly pi. Okay, so that means for each or every strategy of player I, right? So we have the following inequality to be satisfied is that so the expected payoff, okay, for the player I, okay, sum over all the omegas and times the probabilities pi omega, and with utilities for player I, so and other player strategies, and player I's function. Okay, so this should be greater than or equal to. Just copy and paste that, right? So that would be easier. And that will be greater than or equal to the same thing, but changing this sigma I to some tau I, right? As we mentioned before. So that would be some deviation by player I unilaterally by not taking the indicated function, right? Which is given by this sigma. Okay. So, and we need to notice that the probability space and the information partition, they are part of the equilibrium. Okay, so those are not exogenous. So, which is quite different from the previous case there, where the for the mixed strategies, but they are which are not the correlated equilibrium, right? So this inequality is equivalent to the requirement that for every state omega that occurs with some positive probability that the action sigma I is optimal, given other player strategies and player I's knowledge or the information about omega, right? Okay, so as we mentioned, so you might already see that this correlated equilibrium is sort of a more general solution concept than mixed strategy Nash equilibrium, right? So so next we're trying to prove that for every mixed strategy Nash equilibrium, so it's so that would be also a correlated equilibrium. Okay. So the sketch or the idea of that proof would be just to construct a mixed strategy Nash equilibrium and to be a correlated equilibrium, right? So for any of those things. Okay. So now let's first give the proposition. Okay. So for each mixed strategy Nash equilibrium alpha of finite strategic gain, okay, and AI UI, right? So there will be a correlated equilibrium okay, so which a tuple with first omega and pi together and this partition and some function, okay, where for each player I, the distribution AI induced by sigma I is alpha I. Okay. Okay, now let's begin the proof. Okay. As we mentioned, so idea would be just the construction, right? So let's just define narrowly, okay, to let the state space to be just action space, okay. Then you already see that we just define as small as possible for this state space to be the action space, and we can just establish the equivalency of those things, right? So this A is just the product of those AJs, right? And also define this pi, okay, pi A would be the product, okay, over the J's of the alpha J's with some for some AJ, right? For some action. Okay. So this pi A, this is the probability measure for the in the correlated equilibrium, right? And this would be the probability that we previously see from the mixed strategy Nash equilibrium. So for each, okay, I and some bi, okay, let p bi. So we're going to define the partition, right? So the element of partition pi, given some bi, this action would be just some element in A where this AI is bi, okay? So we define exactly for the partition of that for the action bi to be those elements that are equal to this bi and those elements in the set of this action space A, right? So, and further, let this curly pi consists of the cardinality of AI sets. So that number of sets pi bi, okay. So the reason why we're doing this is because remember in the battle of sexes, then each player has two possible actions, right? So so we just separately, we just respectively to define each action into one partition. Okay, so that's the meaning of that. Okay, just put one action to one partition. Okay, so in this case, then the partition would be pretty straightforward, right? So it's very clear for the players to follow which is which, right? So they know exactly. So there will be no confusion about some mix of those states in some sets for the partition, right? So they'll be very clear. So each partition only has one element. So that's why we're saying that this PI consists of the AI coordinative AI sets of that, right? Because in this case, we only need to show that the mixed strategy Nash equilibrium is also a correlated equilibrium, right? So we just make everything to be clear as possible, right? To be the smallest and most efficient. Okay, so okay, further let or define sigma I by sigma I A equals to AI, okay? So that's also very straightforward. So it means that the function for player I from this A, okay, just maps to this this AI. Okay. for each A in the action space. Okay, then so that's we can already see that, right? So this is just a correlated equilibrium, right? So we have constructed this according to all those requirements. So then this tuple omega pi curly p sigma phi, so this is a correlated equilibrium, right? So the reason is that it satisfies the inequality that we mentioned, right? Okay, since the inequality is satisfied, right? For each strategy deviation tau, right? So left hand side of that inequality right here, okay, is player I's payoff in the mixed strategy Nash equilibrium alpha, and the right hand side is the payoff when this player is using the mixed strategy where the player is choosing some deviated action tau with probability alpha, right? So that's essentially the proof of this. Okay. All right. So now let's go back to the example of the battle of sexes that we mentioned in the beginning, and show some numerical results or numerical example of that. Okay. So let's change the color. So example, battle of sexes. Okay. So there are three mixed strategy Nash equilibrium, right? Because of those two pure strategies could be also regarded as a mixed strategy Nash equilibrium. So the payoffs, okay, from the mixed strategy Nash equilibriums are that 2-1, 1-2, and another mixed one, right? 2/3. Okay. All right. And in addition, so one of the correlated equilibria has the payoff profile of 3/2 and 3/2. Okay. Also, one of the CE, so just the short for the correlated equilibrium, so has a payoff profile and 1.5. Okay, so let's just let omega state space, all right, to be x and y. Okay. And the probabilities are 50-50. Okay. So the partitions for the two players, man and woman, are the same. So they have exactly the same partition. Okay, Bach or Stravinsky. Right. So that's not Bach and Stravinsky yet, right? So those are just some state. Okay, like this would be like sort of a sunny or rainy. Okay. So this is not Bach and Stravinsky yet. So the function maps this sunny x to Bach and maps rainy to Stravinsky. Okay, and this is true for both players. Okay, all right. So then in this case, we can verify that in this case they have an equal probability of having x and y, then given the payoff table from the battle of sexes, then can verify that they have this payoff profile, right? So one of the interpretation of this correlated equilibrium is that the players, they observe the outcome of a public coin toss. Okay, so or like a rain, weather, right? So basically the same thing from nature. So which determines which of the two pro-stratus Nash equilibria they play, right? Okay, so that's the example of battle of sexes, right? Okay, now let's move on. Okay, so we mentioned this is only one of the correlated equilibrium, right? So implicitly, so you might already guess that there might be multiple correlated equilibrium of some strategic game, right? So, and indeed, yes. So actually, we can prove that any convex combination of some correlated equilibrium payoff profiles would be also a correlated equilibrium payoff profile. Okay. Okay. So this would also be a proposition. So let this game to be a very simple strategic game. Okay. So any convex combination of CE payoff correlated equilibrium payoff profiles of this G is also a correlated equilibrium payoff profile of this G. Okay. All right. Okay, now let's prove that. Okay. So let's suppose payoffs U1 ... up to UK. Okay. Be some correlated equilibrium payoff profiles okay, and let some weights for those use. We use lambdas as mentioned in the textbook. So lambda 1 lambda k, okay, from real k, with a valid probability measure. So it means that this lambda k is non-negative for all k, and the summation of those lambdas equals to 1, right? This should be a capital K. All right. Okay, so for each value of K, we make a correlated equilibrium where we have the notation for that. So omega K, pi K, okay, correspondingly curly P I K. So this K is just a superscript for to denote different sort of a different equilibrium, right? B A C E, which generates payoff profile UK. Okay, so those UKs are the payoff profiles, putting all those payoffs for each player together, right? So without loss of generality, we assume that the sets omega k, they're disjoint. Okay. Omega k are disjoint. Okay. All right. So then the following defines a correlated equilibrium. Okay. For which the payoff profile is, we just multiply. Okay. All right. Let's just take the notes first. So the following defines a correlated equilibrium for which the payoff profile is something looks like this. So the summation over k about all those expected UKs, right? Lambda k times UK. Okay, so how do we do that, right? So just let omega to be the union of all those omega k's, right? And for any omega, define some pi of omega equals. So this pi omega is the probability measure for this correlated equilibrium together, right? For that equilibrium. So this is just defined as the pi k for each of those, right? And times the corresponding widths, okay? Where k is such that omega is an element of omega k, okay? So, and further for each I, we let the partition pi, curly pi, to be the union over k of all those pi k's. And also finally, define the function sigma I such that sigma I omega is exactly the same as sigma I k omega. Okay, so it doesn't have to be different. So where k is such that omega is element of omega k. Okay, so then in this way we have all those to define a correlated equilibrium for which the payoff profile could be something as this, right? Then that completes this proof, right? So basically we could interpret the correlated equilibrium just constructed in this proof as follows. So first, a public random variable or a random device or machine determines which of the k correlated equilibrium is to be played, and then the random variable corresponding to the kth correlated equilibrium is realized, actually, right? So let's write down that note, interpretation. Okay. So first, a public random device or machine determines which of the k is correlated equilibria is to be played, right? And then the random variable in the state corresponding to the kth CE is then realized, right? So that will be a very useful, helpful explanation or interpretation of this proposition, right? Okay, good. So then this completes the there are some remaining very useful propositions on the textbook in this subsection, but we're not going to cover that. Okay, so basically those are the most important results that we need to know during the studies of the correlated equilibrium. Okay, all right.